Hi there. So today I want to talk about self-assembled monolayer films. Here's an artist's conception of what they might look like, obviously. This sunny, beautiful clouds in the background. Um, our history and study of self-assembled monolayer films actually begins kind of a long time ago in 1773. And Benjamin Franklin, he dropped about a teaspoon of oil onto a pond, and he noticed that it calmed the waves over a large distance. And of course, this is because the oil didn't blend with the water, but spread out over the top of the water and formed a film on top of it. You can see this sometimes in mud puddles, as in this image here, Oil on Water by Alice. Beautiful thin film interference going on there. Now, Lord Rayleigh, he later calculated that Ben Franklin's films could have a thickness of only one molecule, or be one monolayer thick. And without any formal training and doing her experiments in her own kitchen sink, this lady, Agnes Pockels, she showed that the area of the film can be controlled with barriers. And she added that the surface tension varies with the contamination of the water. And she tried different oils to deduce that the surface pressure couldn't change until the area was confined to about 0.2 nanometers squared. And then this work was originally written as a letter to Lord Rayleigh, who then helped Agnes to publish her work in the journal Nature in 1891. Now, she never received formal appointment, but she published a number of scientific papers, and eventually she received recognition as a pioneer in this new field that was developing called surface science. And in 1931, together with Henry DeVoe, Pockels received the Laura Leonard Award from the Colloid Society, and in the following year, she received an honorary PhD. Now, Pockels' work was furthered by Irving Langmuir, who you might have heard of. With a new experimental apparatus, he proved that the films were monolayers, and that these monolayers were oriented such that the active or most hydrophilic portion of the surface molecules are in contact with the liquid below, whereas the hydrophobic portions of the molecules are pointed up in the air. Now, if you're not familiar with those two words, hydrophilic means water-loving, and hydrophobic means water-fearing. Catherine Blodgett, who was Langmuir's student at the time, described in 1935 the deposition of hundreds of layers of molecules onto a solid substrate in a very ordered fashion, and she made final developments to the Langmuir-Blodgett trough, as it came to be known, allowing it to be used to easily transfer films to solid surface. And here's a picture of Langmuir. He won the Nobel Prize in Chemistry in 1932 for his work in surface science, and this is a picture of Blodgett working with the trough that she helped develop. Now, Langmuir-Blodgett films, as they came to be known, are these monolayer films that form on the liquids. And when a small amount of an insoluble liquid, like oil, for example, is poured onto another liquid, it spreads out across the surface. Now, if you have instead an amphiphile, which is a hydrophobic and a hydrophilic end, then what happens is when that's poured onto water, the hydrophilic end will stay next to the water, and the hydrophobic end is repelled by the water, so it turns and orients itself so that the water-fearing side is away from the water. That makes sense, right? And if you increase the packing of the film, these molecules are going to stand straight up so that the water-loving end is next to the water and the water-fearing end is standing up. And that only happens when you increase the packing to a certain density. Now, for very small concentrations, the surfactant molecules actually exhibit a random motion on the water-air interface. And if you didn't know, a surfactant molecule is one with a hydrophobic and a hydrophilic end, like soap, for example. Now, this motion can be thought to be similar to the motion of ideal gas molecules in a container. The corresponding thermodynamic variables for the surfactant system are surface pressure, surface area, and the number of surfactant molecules. The system behaves similarly to gas in a container. So the density of the surfactant molecules as well as the surface pressure increases upon reducing the surface area A. And further compression of the surfactant molecules on the surface shows behavior similar to phase transitions. So you have, for low packing, a gas that gets compressed into a liquid and ultimately into a perfectly closed packed array of the surfactant molecules on the surface corresponding to a solid, okay? And that's depicted here in this little cartoon. Now, this upright configuration is favored because the end groups, the hydrophilic end wants to be next to the water and the hydrophobic end wants to be away from it. But the ordering is also helped by that chain-chain interaction, okay? And remember, if you have two polymers or two long-chain films, hydrocarbon molecules that are sitting next to each other, when they interact with each other, their neighbors, they interact via weak van der Waals bonds. And those weak bonds, weak interactions are maximized when those chains are aligned. Because the longer the chain, the stronger the interaction between neighboring chains, because you have more atoms in the neighboring chains interacting with each other via those van der Waals bonds. And that's depicted here in this little cartoon. Now, when you push a planar solid into the water, you get a meniscus, okay? If the surface is hydrophobic versus hydrophilic, the meniscus is going to be in different directions, okay? So you can see here, this is a hydrophilic surface, a water-loving surface, and the water wants to creep up, and so the meniscus is upwards. And if you have a hydrophobic surface, the water wants to stay away from that surface, and so it moves downwards away from it. And that's the meniscus depicted in the bottom cartoon, okay? Now, a Langmuir-Blodgett film is going to ride up that meniscus. So if you slowly drag, say, your glass slide or whatever up, okay, and it's hydrophilic, or slowly push it in, so it's hydrophobic, you can transfer that thin film to the solid material, and that forms a Langmuir-Blodgett film. So this is how they form these films. They put the liquid over top of the water, okay, inside of a container holding the water, and then they pushed a slide or some other kind of material into the water, and the Langmuir-Blodgett film transferred itself to the slide instead of being sitting on the water surface. You can also dip them more than once. Okay, and if you dip them more than once, then you can build up one monolayer at a time these Langmuir-Blodgett films so that you have a thicker film. Okay, you can build them up depending on what your surface is like on upstrokes or downstrokes. Okay, and so you can go down, you can go up, you can do all kinds of different things. And this is kind of cool. You can see in these little slides that have been prepared using Langmuir-Blodgett technique the different thicknesses. Remember, you get thin film interference in physics, and the color of the film is dependent upon how thick it is, and that's shown here. And here's a little cartoon of the Langmuir-Blodgett trough that Blodgett helped develop. So basically, you have this amphiphile monolayer, which is shown here in the little cartoon, the little squiggly things sticking up. You have your liquid subphase, which is down here. You have your whole Langmuir-Blodgett trough, which is a container that holds your liquids. You have your solid substrate in, and that's 4 right here, so that's your slide or whatever. Number 5 is the dipping mechanism, so you have some way to control the rate of the dipping. Maybe it's on a spring. I'm sure at first they just did it by hand, but whatever. Okay. You have your plate, your Wilhelmy plate, which measures the monolayer's effect on the surface pressure of the liquid. Okay. You have an electrobalance, which keeps your surface pressure constant when you push it. Okay. Push the barrier, which is 8, which is activated by 9, the barrier mechanism. And then often if you want to make your film nice and uniform, you want to reduce any outside vibration, so you might have a vibration reduction system. And if you want your films to be absolutely perfect, then you need to do it in some kind of clean room. Of course, you saw from the earlier pictures, that's not how they did the first ones in the 30s. They just had an open trough and Blodgett sitting there working with it. So you can get films that are less than perfect just by doing sort of a desktop experiment. These are actually pretty difficult films to prepare, and they're easily scratched off, and they're not very rugged for most purposes. So although Langmuir-Blodgett Films laid a lot of important groundwork for the study of monolayer thin films and their effects, now we use something else, and this is called self-assembled monolayers, or SAMs for short. So these SAMs are stronger, they're easier to make, and you can use a wider variety of starting materials. Like you can put them down on a metal surface like silver or gold or copper. You can put them down on a semiconductor like germanium or silicon or gallium arsenide or silicon dioxide. Now, Langmuir-Blodgett films and SAMs have a lot in common, and the main difference is, though, that the head groups are chemisorbed for a SAM, right? So it forms a chemical bond between your surface and your monolayer film, whereas in Langmuir-Blodgett films, it's just physisorbed, okay, which is why they're not as rugged as the SAMs. Okay, well, how do you make a SAM? It's actually really pretty easy. You just form a liquid solution of whatever monolayer that you want to deposit, and you put that in a beaker with whatever solid surface that you want to deposit on, and you wait. And over time, the chemical reactions happen, and the SAM just packs itself in. So SAMs are created by the chemisorption of those head groups onto a substrate. You can do it in either a vapor phase, say in a vacuum chamber, or just in a beaker inside your fume hood in the liquid phase. And the tail groups organize. So initially, there's a small molecular density on the surface, okay? So only a few stick down at a time. There's a sticking rate, there's a desorption rate, so it can take a while. But these adsorbate molecules form either a disordered mass of molecules or they form an ordered two-dimensional line down phase when the coverage is low, okay? And then as they continue to react with the surface, they continue to chemisorb and get to higher molecular coverage. Over a period of minutes to hours this happens. It begins to form these little three-dimensional crystalline or semi-crystalline structures on the substrate surface. So you'll get little islands forming. And then areas of these close-packed molecules nucleate and grow until the surface substrate is covered in that single monolayer. Now, these adsorbate molecules adsorb readily because they lower the surface free energy of the substrate, and they're stable due to the strong chemisorption of the head groups. So selecting the type of head group depends on what application you want for your SAM. Typically, the head groups are connected to a molecular chain, a long hydrocarbon chain, in which the terminal end can be functionalized. So you can add a hydroxyl group, an OH group, you can add a methyl group, a carbon with 3 hydrogens, you can add an amine group, nitrogen, 2 hydrogens, or an organic acid, COOH, or a thiol group, which is a sulfur and a hydrogen. And that varies the wetting and the interfacial properties. It just kind of depends on what you want. Do you want it to be hydrophobic? Do you want it to be hydrophilic? Do you want it to react with something and pick up molecules? What do you want? Okay, and you choose your end group so that that's the case. An appropriate substrate is then chosen to react with the head group. And substrates can be planar surfaces like silicon or metals, or curved surfaces like nanoparticles. Okay. Alkane thiols are one of the more commonly used molecules for self-assembled monolayers. And alkane thiols are molecules that have an alkyl chain, that long carbon chain, as the backbone. And oftentimes that's represented by that little squiggle line due to what the angles are for the carbons bonding to one another. And then they have a tail group, as we've discussed, one of the hydroxyl, methyl, so on and so forth tail groups. And then they have a thiol group, a sulfur hydrogen head group that likes to react with the gold. And here you can see the gold alkane thiol has been studied a lot. And here you can see the alkane thiol embeds that terminal sulfur atom in a hollow between the triplet of gold atoms. So you can see how that happens there. Here the gold atoms are, of course, gold, and your sulfur group is orange, and then your hydrocarbon chain is coming off that in the gray. Okay. Now they pack at 1/6 of the available site, and they form a hexagonal close-packed layer that has a spacing of about ½ nanometer. And the sulfur gold bond has an energy of about 44 kilocalories per mole. Before you do this reaction, you have to clean your surface really carefully or freshly deposit your gold. Okay, otherwise it might oxidize a little bit and you won't get the nice adsorption otherwise. You'll still get some, but it won't be as perfect. And then the films form in minutes or hours. Now, like we said, van der Waals bonds are going to form between those neighboring alkane thiol chains, and they have a weak strength, about 1.75 kilocalories per mole. The chain spacing is larger when it's just adsorbing onto the gold surface, right? So if you can see that it adsorbs in those little hollow sites in the gold, and what the unit cell spacing is, that's a little further apart than the ideal distance that's needed to maximize that van der Waals interactions between the chains. And so what happens is, to maximize the bonds, they kind of fold down so that they hit their neighbors more closely. And that angle of tilt is about 30 degrees from the normal of the surface. And that maximizes the molecular interactions between the carbon chains as they pack into that crystalline monolayer. And the importance of the van der Waals interactions between the chains is also seen if you think about the chain length. In general, the longer you have your chain, the more ordered the monolayer. And that's because for a longer chain, of course, you get more van der Waals interactions between neighboring chains. Now, what are SAMs used for? Well, a lot of things. SAMs are inexpensive and they're versatile surface coatings for a lot of different applications because simply changing the in-group, you can control properties like wetting, adhesion, chemical resistance, biocompatibility, sensitization, and molecular recognition for sensors and nanofabrication. A whole host of applications. So SAMs can also be used to modify the surface properties of electrodes for electrochemistry, general electronics, and various NEMs and MEMS. What are NEMs and MEMS? We'll get to that in a minute, but those acronyms stand for nano-electrical mechanical systems and micro-electrical mechanical systems, basically nanomachines and micromachines. SAMs can also serve to protect metals from harsh chemicals and etchants, and they can reduce the sticking of NEMs and MEMS components in humid environments. In the same way, SAMs can alter the properties of glass. So a really common household product, you might have heard of it, Rain-X, it utilizes SAMs to create a hydrophobic monolayer on car windshields that helps keep them clear of rain. In other words, it makes your windshield hydrophobic. Now, these next couple of slides I borrowed because they're just so beautiful and they couldn't be improved upon. So I'm going to congratulate Mr. Rashid here on his work. But one of the nice applications of SAMs might be lubricants for micro and nano machines. Now, you'd think that in a micro machine that the friction maybe wouldn't be as big a deal. But it turns out that the weak forces, the van der Waals forces, capillary forces, that you can pretty much ignore in large machines totally gum up the works when you try and scale that same idea down to the micro and nano scale. So here you can see some images of micro machines that people have actually built. Here's a little series of cantilevers, and here's some little micro scale gears. But these little gears seize up, and the little cantilevers kind of just on their own stick down when you start walking their sides down and down and down, because these what are weak forces on the macro scale start to really dominate when the mass of your object is tiny. Well, you can't use conventional lubricants like oil, okay, or something like that. That would just totally gum up the works of these little nano and micro machines. And so instead, you need to get creative about what kind of lubricants that you might use. So one of the possible candidates for anti-stiction in MEMS devices to reduce sticking, which they call stiction as opposed to friction, isn't that cute, is to deposit these self-assembled monolayers down on the surface. And it really helps if you choose the right in-group in keeping these things from just automatically sticking together. Another possibility that gets used a lot are these diamond-like carbon coatings that are tough. Another potential application that was discussed in the scientific literature for these self-assembled monolayers are for microfluidic devices. Okay, so microfluidic is exactly what it sounds like. You have a little microchannel through which fluid flows. Okay, thin film SAMs can be used and placed on nanostructures in microfluidic devices, as this group discussed in their 2009 paper. So what they do is they functionalize, the SAMs functionalize the nanostructure. And this is advantageous because the nanostructure can now selectively attach itself to other molecules or SAMs. And this technique is useful in biosensors or other MEMS devices that might need to separate one type of molecule from its environment. So one example is the use of magnetic nanoparticles to remove a fungus from the bloodstream. So the nanoparticle is then coated with a SAM that likes to bind to the specific fungus that they're trying to get out. And then if you want to filter out your contaminated blood, maybe using a little injectable MEMS device, for example, the magnetic nanoparticles are inserted into the blood, and then they bind to that fungus, and then you can magnetically drive them out of the bloodstream by sort of exploiting the magnetic properties of your nanoparticles. And you can divert that fungus into a waste stream, and then you put the clean, nice, happy blood back in. Okay? They do kind of something similar if you get heavy metal poisoning. Now, it's actually, this process is called chelation if you want to look it up. Now, a little bit more in microfluidics just because it's so fun. Of course, you can look this up. ufluidics.com is one company that sells microfluidics devices. Now, most of these devices haven't made it to the injectable MEMS stage yet, unfortunately, which would be super cool. But most of them that are on the market now are for diagnostic, forensic, or research purposes. So, in other words, you put your blood or whatever your fluid is through this microfluidic channel. Maybe you use some SAMs, maybe you use some nanoparticles or whatever, and then your results come out the other side. So maybe instead of getting rid of the fungus, you're testing to see whether someone's blood has the fungus in it, and that would be maybe the diagnostic purposes. Or maybe you're at a crime scene and you want to know if this person was killed with heavy metal poisoning. I don't even know what possibly you might do, and then you put you put your blood through the microfluidic device and diagnose how the person died or something like that. Okay, so those are some of the applications for these self-assembled monolayers. And yet again, this is continuing our discussion of self-assembly as a bottom-up approach to nanotechnology. I hope you enjoyed it, and I'll see you next time.